Welcome to the 12th class of this course. At first, let me summarize what we have done in the past few classes. Okay, so what we did is basically we took the Lagrange's differential equation. This is Legendre differential equation. This is the Legendre differential equation, and we solved it. We got the general solution, and from there we truncated the two independent solution two independent series solution we got, and we truncated that for integer values of L, and we got the Legendre polynomials. These are the Legendre polynomials, and then we showed that the same Legendre polynomials, those can be generated using this Rodriguez formula. And also in the last class what we showed is basically the same Legendre polynomials can also be generated using this generating function. Okay, and in this class I will prove some recurrence relation or recursion relations using this generating function. Okay, so this generating function will be very important, and remember the generating function is a function of x and h, both are variable here, and we will get the Legendre polynomials as the coefficients of this power series expansion of h. Okay. Power series expansion of this generating function in h. Okay, so now let's look at this recurrence relation. So there are 6 recurrence relations I have noted down, but there can be a lot, there can be a lot. So I will prove these 6 in today's class. If time permits, I will prove all these 6 recurrence relations. So let me start with the first one. Okay, recurrence relation A. It's written that L PLX, this one, equals to 2L minus 1 x PL minus 1x PL minus 1x minus L minus 1 times PL minus 2x. So L minus 1 times PL minus 2x. So it basically connects the L minus 2 and L minus 1th Legendre polynomial with Lth Legendre polynomial. Okay, so if it basically says if one knows L minus 1th and L minus 2th Legendre polynomials, then how can he get he or she get the Lth Legendre polynomial? Okay, so let's start with the generating function. Phi as a function of x and h equals to 1 by root under 1 minus 2 xh plus h square, and it equals to sum over plx h to the power l equals to 0 to infinity. Okay, so now I will not prove all the steps. Okay, I will give you a little homeworks which I think you can do using your just 10 plus 2 calculus. So prove using that phi of xh equals to 1 by root under 1 minus 2 xh plus h square. So consider this and prove that 1 minus 2 xh plus h square times del phi del h, okay, it's a partial derivative of phi with respect to h, equals to minus h minus x, or rather x minus h phi. Okay, prove it. So you need to do the partial derivative of phi with respect to h, and then you will see that okay, this relation follows. Okay, so prove it. prove it. Homework. And now why we are doing this? Why you are doing this del phi del h? If you look at this recurrence relation, so you can see that there is no derivative with respect to x, right? So there is no p dash l or l minus 1 or l minus 2, but there are terms like p l minus 1, p l minus 2. So the idea is basically, so this kind of so if I try to derive this recurrence relation from this generating function, then we basically need to deal with this kind of this kind of series expansions, of with respect to h. Okay, and what we need to do is we need to compare the powers of h to the power l, right? So here basically this index, l minus 1, l minus 2, instead of pl, these indexes are changing. Okay, and now if we try to do that, if we try to do that, so somehow we need to so here if you look at this relation, there is a index of power of h and this index of p, that is pl, those are same basically. So somehow we need to create a mismatch between these two. Okay, and that can be done by differentiating this phi with respect to h. So then there will be a mismatch of then h can reduce one power. H to the power l can be reduced to h to the power l minus 1. Okay, and this kind of mismatch between power of h and this index of p, that can be done. And after that, if we compare the same powers of h, then basically we this kind of pl minus 1 and pl, so they will come in the same in the coefficient of same h to the power l. So that's the idea of this differentiation. Okay, so if you have not understood it, let me solve it, and you will gradually understand what I'm trying to say. So now what I will do is, now I will use this, so phi as this sum over plx h to the power l. Okay, if I do that, then basically it is 1 minus 2 xh plus h square, and del phi del h, which is nothing but sum over l equals to 0 to infinity plx. I will write as it is because it's a function of x. Okay, and it's a partial derivative with respect to h, so it will only affect this h to the power l term. And so if I do del h of h to the power l, which is nothing but l times h to the power l minus 1. Okay, and it equals to minus, or let me write it as x plus x minus h. It is x minus h times sum over l equals to 0 to infinity plx h to the power l. Okay, and now if I simplify it, if I remove this bracket and multiply this with each term, then what we get for the first term, I will get l equals to 0 to infinity plx, let me write l here, h to the power l minus 1. Okay, now in the next term is basically minus twice x sum over l equals to 0 to infinity l plx h to the power, so here there is one h and here h to the power l minus 1. So if I multiply them, it will be h to the power l, h to the power l. Okay, and the third term, it will be plus sum over l equals to 0 to infinity plx, let me write this l here, l times plx, h to the power l plus 1, because here there is h square and here h to the power l minus 1. and now the right hand side will be equals to the right hand side will be x times sum over L equals to 0 to infinity PLX h to the power L minus sum over L equals to 0 to infinity PLX h to the power L plus 1. Okay, and now I will take these two terms from the right hand side. I will take them to the left hand side. Okay, so then what will be the terms? It will basically, the first term will be as it is, because here h has a power of h to the power L minus 1. Okay, h has a power of L minus 1, so that I will keep it as it is. So it is L PLX h to the power L minus 1, L equals to 0 to infinity. And if I take this term in the left hand side, then it will be, so it will be, so these two terms I can put them together. Okay, this term and this term, right? So here x I can take common, so it will be minus x. Okay, sum over L equals to 0 to infinity. I can take this PLX and h to the power L also common from these two terms, you know, and then we are left with then twice L plus 1. Okay, so twice L is coming from this twice L, and here from this term there is, I mean, multiply. If I take x and this common, then this 1 will come. Okay, and now these two terms, see, I will take this in term from the left hand side to, from the right hand side to left hand side, and I will make so I will treat them in the same bracket, put them together. So because here h has a power of, in both of the terms h has a power of L plus 1, right? So if I do that, then it is basically nothing but sum over L equals to 0 to infinity L plus 1 times PLX h to the power L plus 1 equals to 0, right? So this L is coming from here and 1 is coming from here. Good. Now you cannot still compare the powers, right? Because here h has a power of, here h has a power of L minus 1, here h has a power of L, here h has a power of L plus 1, right? So what you need to do is basically make, so do the index shifting and make them, you know, all of the terms should have the same power of h. Okay, now if you look at the recurrence relation here, you know, the first term is LPLX, right? And you can see here we already got this term LPLX. Okay, now if I do, if I do the index shifting in this term and make it look like h to the power L, then these terms will change, but we don't want that, we already got that term. Okay, right? So what the idea is, basically we will not change, we will not do the index shifting for this term. Instead of that, for all these two terms we will do the index shifting and write it like some factor times h to the power L minus 1, and this term also some factor h to the power L minus 1. Okay, and then we can put them together. Okay, that's the idea. So this term we will not touch because we already got, this is what we need to prove, right? Fine. So let me then deal with first this term. Okay, which is, okay, I'm writing it in blue, which is x sum over L equals to 0 to infinity 2l plus 1 plx h to the power l. Okay, and now I will do the index shifting in such a way that this h to the power l, it comes down to h to the power l minus 1. Okay, so what basically I will do is I will treat l as m minus 1. Okay, so in that case l starting from 0, so if l equals to 0, it means m equals to 1, right? And l tends to infinity will mean n tends to infinity, right? So if I now do the index shifting, then it will be x times m equals to 1 to infinity, and instead of l I am writing m minus 1, so it will be 2 times m minus 1, which is 2m times 2m minus 2, and there is a plus 1 here, so it will be 2m minus 1, right? It will be p m minus 1x h to the power l, sorry, h to the power m minus 1, m minus 1. Okay, and now as m is a summation index, I will write it as sum over l equals to 1 to infinity, and I will encourage you to do this index shifting by yourself, because we already did a lot of index shifting in this course, so I think you should be able to do it by yourself. Okay, so this term, for this term it is done, and let me now take care of this term. Okay, here also we want it to write it like sum over and some factors times h to the power l minus 1. Okay, so I will do that in green color. Okay, this sum over l equals to 0 to infinity l plus 1, right, plx h to the power l plus 1 equals to, okay, not equals to, and now here instead of l plus 1, I want l minus 1. Okay, so the index shifting will be like l plus 1 equals to m minus 1. Okay, so in that case, but basically it's like l equals to m minus 2, right? So if l equals to 0, it means m equals to 2, and if l tends to infinity, m will also tends to infinity. So if I do the, so it will start from m equals to 2 to infinity, and then l plus 1, instead of l plus 1 I will write m minus 1, then p of m minus 2 x, instead of l I am writing m minus 2, and it will be h to the power m minus 1, right? And then as m is a summation index, I can write it as l, so I can just write l instead of m, l minus 1 p l minus 2 x h to the power l minus 1. Now still the problem hasn't solved entirely, because here the summation is starting from l equals to 2, here the summation is starting from l equals to 1, right? Here the summation is starting from l equals to 1, here it is starting from l equals to 2, and here it is starting from l equals to 0. So still we cannot put them together, but if you notice closely, then if I put l equals to 0 for this term, it will, so l equals to 0th term is basically 0, because there is a l factor sitting here. Okay, so instead of l equals to, starting from l equals to 0, I can start it from l equals to 1. That will not change anything, right? And now this term, the blue underlined term, that is already starting from l equals to 1, right? And this green term, I can also write it as l equals to 1 to infinity p of l equals to 1 to infinity l minus 1 p of l minus 2 h to the power l minus 1. Instead of starting from l equals to 2, I can also start it from l equals to 1. Why? I think you should be able to answer that. So if I put L equals to 1, L equals to 1th term, so then because of this factor sitting here, it will be 0. Okay, so it will not, so it will not change anything if I start it from L equals to 1. Okay, these two are basically equal, and now I can put them together. Okay, now you can see that all the terms are starting from L equals to 1. Okay, so if I now put them together, then this line, okay, this one, then the first term is sum over L equals to 1 to infinity L PLX h to the power L minus 1, right, minus this term, which is x sum over L equals to 1 to infinity 2L minus 1, okay, 2L minus 1 P L minus 1 h to the power L minus 1, right, PL minus 1 as a function of x, and plus this term, which is sum over L equals to 1 to infinity L minus 1 P L minus 2 x h to the power L minus 1 equals to 0. Okay, and now what I will do is I will put all of them together, that is L equals to 0 to 1 to infinity, then L PL x minus, I will take this h to the power L minus 1 common, it will be minus x times twice L minus 1 P of L minus 1 x plus L minus 1 P of L minus 2 x times h to the power L minus 1 equals to 0. So it's just like a power series in h, and the right hand side equals to 0. That means all the coefficients will be also equals to 0. If I do that, I will make all of them equals to 0, all the coefficients. That means L PLX minus x 2L minus 1 PL minus 1x plus L minus 1 PL minus 2x equals to 0. And our recurrence relation is proof. That is, then if I take these two terms in the right hand side, then basically we will get L PLX equals to 2L minus 1 times x. Instead of x times 2L minus 1, I'm writing it just, I'm just interchanging it. So L minus 1 x minus L minus 1 PL minus 2 x, and proved. Okay. So I have proved the first recurrence relation. Now let's prove the second one. Okay, so let's go for the second one. The second one is B. Okay, second one is x p dash lx. Okay, x p dash lx minus p dash L minus 1x minus p dash L minus 1x equals to LPLX, right? LPLX. So now you can see that there are derivatives with respect to x are involved here. Okay, so basically what I will do is I will take this generating function, which is nothing but 1 by root under 1 minus 2xh plus h square. Okay, and now I will give you a homework, that is using considering phi as this, prove that x minus h del phi del x equals to h times del phi del h. Okay, homework. You just need to do the partial derivatives, show that okay, this left hand side and right hand side are equal. Okay, homework, prove it or show it. Now so while proving it, you need to consider phi as this. Okay, and once you show it, then I will just write phi, I will replace phi by sum over plx h to the power n equals to 0 to infinity. Okay. So then this term will be x minus h del phi del x. Okay, that means it will be L equals to 0 to infinity p dash lx h to the power L equals to h times del phi del h. So del phi del h is, we have already calculated del phi del h, that is L into plx times h to the power L minus 1 sum over L equals to 0 to infinity, right? And there is h multiplied with it, so it means the whole factor will be then, the whole term will be then sum over L equals to 0 to infinity L plx h to the power L. Okay, fine. Now I will multiply this term with each of these two terms. So if I do that, then it is sum over L equals to 0 to infinity x p dash lx h to the power L. Okay, so I already got, let's see, as a coefficient of h to the power L, I already got this term. Okay, minus h multiplied with this term, which is sum over L equals to 0 to infinity p dash lx h to the power L plus 1. Okay, equals to sum over L equals to 0 to infinity L plx h to the power L. Okay, and this L plx, that is also present here. Okay, so here also as a coefficient of h to the power L we got this term, so these two terms we got. Okay, now what we need to show is that here, so here h is a power of L plus 1, so what we need to do, I think it's very clear, I think that we need to do the index shifting. Okay, and then we need to show that okay, it is indeed, so let me do the index shifting, and then basically as a function, as a coefficient of h to the power L, you will get this term. So okay, let me write and use a different color. So then L plus 1, I will write it as m, then L equals to m minus 1, and if L equals to 0, it means m equals to 1, right? So then it is basically sum over m equals to 1 to infinity p dashed m minus 1 x h to the power L, sorry, h to the power m, h to the power m, and it can also be written as, I can replace m by L, p dash L minus 1 x h to the power L. Okay, so Okay, so basically as a coefficient of h to the power l, I got this p dash l minus 1x. Okay, this p dash l minus 1x, but this series it is starting from l equals to 1, and here this series is starting from l equals to 0, and this one is also starting from l equals to 0, right? So right now we cannot really put them together. Okay, but if you look carefully, there is a L factor sitting here. So L equals to 0th term will contribute nothing for this summation. So I can instead start from L equals to 1, right? So I will start from L equals to 1. Okay. Now here if you see, for L equals to 0th term, what will be the L equals to 0th term? It will be x times p dash 0x, right? H to the power L, h to the power 0, which is nothing but 1, right? And what is p0x? P0x is a constant, that is 1. You already know that. And what is the derivative of it? If there is a constant term, then derivative means the rate of change, but it is a constant, it is not changing, so its rate of change is 0. So that means this term for L equals to 0th term, this is so this term also in this summation, the L equals to 0th term is also 0. So I can start it from, that means this equals to 0, right? So I can start it from then L equals to 1, and now we are done. So now I will put them together. There is L equals to 1 to infinity x p dash x minus p dash l minus 1x times h to the power l equals to sum over l equals to 1 to infinity l plx h to the power l. Okay, and now if I compare the coefficient of h, so this will be equals to this. So basically if I compare the coefficients of h to the power l, then I can show that, I can write that p dash l x minus p dash l minus 1x equals to l times px. Okay, and we are done. This is what we need to prove. Okay, so proved. Now let's look at this recurrence relation number C, which is this one. Okay, so number C. Number C is p dash lx minus x p dash l minus 1x. So p dash lx minus x p dash l minus 1x, okay, equals to L times p of L minus 1x, equals to L times p of L minus 1x. Okay, so let me write down recurrence relation 1 first. Recurrence relation A. What we got from recurrence relation A, that is this one. So L into PLX, L PLX equals to L PLX equals to here. Okay, L PLX equals to 2L minus 1x PL minus 1x, 2L minus 1x PL minus 1x, okay, minus L minus 1 minus L minus 1 times P of L minus 2x, right? So this is the recurrence relation 1 we already proved. Okay, and let me write down the recurrence relation 2 also. Okay, first let me first let me do the derivative here. So if I do the ddx of it, then it is basically L p dash lx equals to 2L minus 1 p of L minus 1x. So I am doing derivative with this of this x, and then I will do the derivative of this term. So it will be then basically plus 2L minus 1 x p dash x L minus 1 minus L minus 1 p dash L minus 2 x, right? Okay, so okay, now we still cannot so there is L minus 2 here. Okay, so p of L minus 2 present here. We somehow need to cancel it because here there is no PL minus 2, right? So to do that, we need to take the help of recurrence relation B. And what is recurrence relation B? This is this one, right? Which is x p dash PL dash x, okay, minus PL minus 1 dash x equals to L times PLX, right? Okay, now what I will do is I will replace this L by L minus 1 because L is just an index, it's an indexing thing. So instead of starting from L, I can just change the indexing, right? So instead of writing L, I can write L minus 1 because L will take the integer values. So it is p dash L minus 2x, and so we got this L minus 2 equals to L minus 1 p of L minus 1x. Okay, this is what I'm doing. I'm just writing L as L minus 1. Okay, and here from here I can show that, okay, p dash L minus 2x equals to x p dash L minus 1x minus L minus 1 p of L minus 1x. So I took this term, so I multiplied the whole thing with a minus sign, whole this line with a minus sign, and then took this term in the right hand side. Okay, so we got p dash L minus 2x. Let me multiply it with L minus 1 also, because here there is L minus 1 multiplied with it. So it is nothing but then p dash L minus 2x equals to x L minus 1 p dash L minus 1x minus L minus 1 whole square, that is L square minus 2L plus 1 PL minus 1x. Okay, and now if I put this value of L minus 1 times p dash L minus 2x here, okay, here, then what we are left with is basically, let me call it equation 1, let me call it equation 2. Okay. Then from equation 1, what we can get is basically L p dash Lx equals to 2L minus 1, right, p of L minus 1x, okay, plus this term which is 2L minus 1 x p dash L minus 1x, right, and this term minus this term, okay, minus this term, and this term is nothing but these two terms. Okay, so minus x times L minus 1 p dash L minus 1x plus L square minus 2L plus 1 times P of L minus 1x. And now if I do the simplification, then I mean these two terms, if I put them together, then this 2L and this minus 2L will cancel, and this minus 1 and plus 1 will cancel. So we are left with L square P of L minus 1x, and here, so we are left with, then if I take this plus x common and then P of L minus P dash of L minus 1x common, then we are left with 2L minus 1 minus L plus 1, right? So from this term and from this term, and here there is a minus sign. Okay, so which is basically minus 1 plus 1 cancel, and then 2L minus L, that is L. Okay, so then the whole term is nothing but L. And now if I divide by L, then it is P dash x. So it is basically L P dash Lx. Okay, and then if I can divide by L, then it is P dash Lx equals to L PL minus 1x plus x P dash L minus 1x. Okay, and that's what we needed to prove, right? So P dash Lx. Okay, I can take this in the left hand side. If I take it in the left to the left hand side, then it is P dash Lx minus x P dash L minus 1x equals to L PL minus 1x, and that's the recurrence relation. So it's proved. So I have proved 3 recurrence relations, and I will ask you to, I will give the other 3 recurrence relations as homeworks. Okay, so prove the recurrence relation, prove recurrence relations D, E and F. Okay, and to prove them, you need to use this recurrence relation C and B. Okay, using C and B, using recurrence relation C and B. So what are C and B? Okay, so for example, I am giving you some hints. Okay, so hints are basically, to prove D, what you need to do is basically take the recurrence relation C and subtract it. So it will be minus x times recurrence relation of B. Okay, so multiply x with recurrence relation B and subtract it from recurrence relation C, then you will get the recurrence relation D. Okay, then for E, what you need to do is calculate x times C. Okay, and then add it with minus B recurrence relation. So I am writing B, and then a circle means it's a recurrence relation. And for recurrence relation F, to prove recurrence relation F, what you need to do is basically take recurrence relation C. Okay, then replace L with L plus 1. Okay, and then add it with B, then you will get recurrence relation F. So these are the hints, and I think you can very easily derive them. These are very easy derivation. Okay, so that's all for today then, and in the next class I will show some physical applications of Legendre polynomials or Legendre differential equations, and after that I will discuss about orthogonality and orthonormality of Legendre polynomials. Okay, bye.